We saw in the warm-up that sometimes the way we define things can vary from book to book, or maybe from class to class. We might define things a little bit differently, which can really have an effect on what it is we're trying to show or prove about something. This is tricky in math, right? Math is built on abstractions. Numbers, sets, functions, and spaces are all really abstract things. They don't really exist like in the physical sense that a lot of other things that that we work with do in school. And so because of this, definitions play a really central role, and they allow us to communicate our ideas precisely. When we're just sort of dealing with everyday life, definitions often emerge from examples, right? So you might notice that like a robin and a sparrow and a pigeon all sort of have these properties in common. And so you kind of call that a bird, and then you attempt to describe the features that make something a bird. Precision maybe is not as necessary there. But in math, the process is a little bit different, right? We create our definitions, which often are guided by examples, but they always have to come with a certain kind of clarity. So when we're coming up with a good definition for something, we need to be able to do two things. The first is we need to be able to capture the intuitive idea that we're trying to formulate. That we are trying, to formalize. We want to capture the intuitive idea, but we also want to make sure that the definition we come up with is rigorous and can be applied in all contexts. So it needs to provide a rigorous standard that can be applied across different contexts. Of course, right, this is challenging as well because I'm sure you've seen in your studies that there are times when you use different definitions depending on different contexts. But we just sort of do the best that we can to come up with something that really captures what we're trying to say and can be generalized. So let's start with looking at polygons as we did in the warm-up problems. A common intuitive idea of a polygon is just a flat shape made out of straight lines. But if we just say that, then that allows for maybe different ideas than what we might expect from a polygon, right? Does a polygon have to be convex, or do we allow for something like this, right? That's a flat shape made out of straight sides, if I drew it correctly. Is that a polygon? Can the sides cross each other, right? Is this a polygon? This is flat, it's made out of straight sides. Does that count as a polygon? And do we require a minimum number of sides? Do you have to have at least 3, or could you say, like, if I go from A to B back to A again, well, it's certainly flat and it's made out of straight lines. Does that make it a polygon? Right? So we want to be careful. We want to make sure we're more precise in order to rule out anything that we don't want to have there. So we agree to precise definitions so that theorems can be proved unambiguously. As an example, if we want to look at theorems about the sums of interior angles of a polygon, I'm sure you've seen the theorem that the sum of the interior angles of an n-gon, the degrees of the measures of the interior angles of an n-gon is n minus 2 times 180, or maybe 180 times n minus 360. But this requires that polygons have non-intersecting sides. So if we want to make sure that we are describing a shape that has a certain property like this, we need to make sure that our definition doesn't allow for any funny business like intersecting sides. So even sort of at a very basic level, we can run into some issues. For example, if we define a square, as we often do, to be a quadrilateral with, we often describe it as having 4 congruent sides and 4 congruent angles. And then we define a rectangle to be a quadrilateral with 4 right angles. So in other words, a quadrilateral with 4 congruent angles only. Then a natural question to ask would be, is every square a rectangle? If we're defining it this way, which is I think the most normal way to define it, then the answer would be yes, except oftentimes, especially in early grades, rectangles are really presented as having a property of having 2 long sides and 2 short sides, right? Something like this. 4 right angles, but 2 of the sides are longer than the other 2 sides. In which case, the answer to this question would be no, right? Not all squares are rectangles. But as our definition had it currently written, we describe a square as having 4 right angles. Then in this case, yes, a rectangle has 4. Our definition of a rectangle has 4 right angles, which means our definition of a square, which says it has 4 right angles and 4 congruent sides, and the answer would be yes here. And so this shows how definitions can influence whether statements are true or false.